Comes on everyone. Let's start off. I hope everyone has gone through the notes. The last thing that we did was a sonometer. We have derived this equation, and this was the main thing, and this is what we're going to play around with. And we have seen what is an overtone, what is a harmonic, how does the number of loops, wavelength, and everything changes. So let's see a few questions on this. We got a block here of density rho b, and it is immersed in a liquid density rho l. This is x is equal to 0, this is x is equal to L, and you're using a tuning fork to generate frequency. Now the string oscillates in second overtone. Hope you remember what is the overtone. The frequency is after the fundamental, right? Before immersing. And third overtone after immersing. Find the ratio of rho b by rho L. Density of the body by density of the liquid. Let's get this thing. Let's see. Right, Samyak. So first thing, what is second overtone and third overtone? So be careful with that. Second overtone is the frequency, second frequency after the fundamental, meaning it is a third harmonic. So n is 3, and third overtone is fourth harmonic. So n is 4. So that is the first thing you need to figure out. So the words, these are important. So second overtone and third overtone. So this was fourth harmonic. And this was third harmonic. And then you're done. So before immersing, the tension was T1 and the weight was rho b Vg. After immersing, forces will be T2, the weight rho b volume G, the bind force will be a rho liquid Vg. So tension will be rho B volume G. Tension T2 will be rho body minus rho liquid volume G. Bind force everyone. And we know the formula F is equal to N by 2L root over T by mu. Now, if you see here, frequency is constant, length is constant, mu is constant. What changes is N into root T. So this will be 3 into root T1 is equal to 4 into root T2. Rho B Vg is equal to 4 into rho B minus rho L Vg. So this would be 9 rho B, 16 rho B minus 16 rho L. So we get rho B by rho L will be 16 by 7. Yeah. Rho B by rho L. So that way. Easy. You just have to use the bind force, get the tension, and put it in the formula there. Any doubts on this? Straightforward, simple equation. So you should know your formula for sonometer and you should know about bind force. Next one. Y is equal to 10 sine pi by 3x plus cos pi by 60. This is the equation of SHM. X and Y are in centimeters. Just to give an idea, if you see our general equation, y is equal to 2a sine kx cos omega t. This was the equation. Find velocity. Acceleration. Of the particle at x is equal to 2 centimeters at time t is equal to 2 seconds. So at x is equal to 2 centimeters, there is a particle. That particle at 2 seconds, what is velocity and acceleration? Find v wave, find max speed, and max acceleration of a particle. Length of the string in sonometer is 30 centimeters. Which harmonic is this? Find phase difference between the particles. X is equal to 2 centimeter and x is equal to 2.5 centimeters. So there are two particles at 2 centimeter and 2.5 centimeters. What is the phase difference between them? X is equal to 2 centimeter and x is equal to 3.5 centimeter. There, get them 4 questions. Yeah, this thing covers a lot. Let's go one step at a time. So first thing, find velocity and acceleration of the particle. It's straightforward, like you want velocity and acceleration, just differentiate it. So velocity v will be dou y by dou t, partial differentiation. So when you do this, the x thing will not change. So this will be 10 sine pi by 3x. This guy is constant. You differentiate the cos function here. That will be minus pi by 6 sine pi by 60. You want acceleration, differentiate velocity again, dou v by dou t. So again, when you differentiate, again, the sign will differentiate. This will be 10 sine pi by 3x. This will become minus pi square by 6 square cos pi by 60. Then you just differentiate. Now put x is equal to 2 and this thing, and you'll get your answer. So substitute x is equal to 2 and t is equal to 2. Then you'll get the velocity and you'll get the acceleration. So yeah, that you can handle this. What was the second question? Find v wave, maximum speed, maximum acceleration. We can clearly see in this function, this value is 2 times amplitude. This guy was omega, this guy was k, and this guy was omega. So v wave is nothing but omega by k. So substitute there. That would be how much? Pi by 6 by pi by 3. So that's half meter per second. Right? And what do you want to find? Maximum velocity? Go to SHM. If you remember, maximum SHM formula, it is A into omega. What is A there? A is the maximum amplitude. In a stationary wave, what is the maximum amplitude? Two-way, antinode. So the particles at the antinode are going the fastest. So among all the particles on a stationary wave, the antinode particles have the maximum speed and the maximum acceleration. Right. Similarly, what is the maximum acceleration? A omega square. But A ka place mein we have 2A. I hope you're getting that. So this value is 10. So 2A is the maximum amplitude of the particle. So and you can get the C part also. What is the wavelength? K is equal to pi by 3, which is equal to 2 pi by lambda. So we get lambda is equal to 6 meters. So what is the length of one loop? Length of a loop is lambda by 2. 3 centimeters. And how much was the length of the string? Length of the string was 30 centimeters. So if 3 centimeters is one loop, then the number of loops are 10. This is a 10th harmonic. I hope you're getting what you're doing here. Like from the equation, you're just playing around. It is still an SHM. So all these waves are nothing but a bunch of particles oscillating in SHM. Have a look at ABC. So you have an equation, you can mine data from there. Get the D part, that's a good one. That's a really good mains level question. But any doubts on ABC, please ask me. So be careful about that maximum speed and all. The formula is still valid for an SHM. The maximum speed of a particle is A omega. But A is the amplitude of a particle. And in a stationary wave, the antinode has a maximum amplitude, which is 2A. So don't get confused between that A thing. So that single A was the amplitude of the initial waves. So when you're sending two waves, the maximum becomes 2A there. What about the D part? But D part, one thing is this. If you remember the formula, phi is equal to 2 pi k delta x. is equal to 2 by lambda delta x. Don't use this. This is a wrong. This is valid for progressive waves. You should not use this formula for a stationary wave because stationary wave is a combination of two progressive waves. This formula we derived for a progressive wave. So this is the most common mistake what people do. They use this formula, they put the numbers and they'll get an answer and they get trapped. Then how do we do this? If you look at the wave, this thing I drew the picture last time we did discuss this. If you look at the particles, how are they moving? All the particles in a loop are going in phase. Remember this? We wrote a statement there. Means all the particles in this guy are going up and coming down together. All the particles in the second loop are going down together. All the particles in this loop are going up together. So now what you need to check is where is your point? Now we know length of one loop is 3 centimeters. So this was x is equal to 0, this was x is equal to 3, and this was x is equal to 6. So x is equal to 2 will be somewhere here. X is equal to 2.5 will be also somewhere here. And x is equal to 3.5 will be somewhere here. So all points in a loop or alternate loops, alternate meaning 1, 3 and all, the phase difference will be 0. So that means for the point x is equal to 2 and x is equal to 2.5, the phase angle is 0. So be careful. You can't use that formula. So here you get only two answers. Either you'll get 0 or pi. There is no other option for stationary waves. And if you look at x is equal to 2.5 and 3.5, the points in consecutive loops are out of phase. So you need to ask yourself, where is the point? X is equal to 2 and x is equal to 3.5. They're out of phase. So phase difference is pi. Are you clear with this? So be careful with this. So always ask yourself, am I talking about a progressive wave or a stationary wave? How does a progressive wave look like? Y is equal to a sine kx plus or minus omega t. This is the progressive wave. Look at this thing. This is sine kx cos omega. This is not a progressive wave. The kx and omega t got separated. So that's the difference. You have to be careful there. All clear with this? So that's one important thing. So are you dealing with a progressive wave or a stationary wave? So that is a good trap. People will blindly do that formula and then they get it wrong and then they don't understand why. Because stationary wave is not one wave. It is a combination of two waves. The whole thing has changed. Let's see one more. So if you see, right, you're just playing with that one equation and that formula. The main thing is that if you see some 10, 12 problems, you'll get the hang of it. It's not really that tough, but you should have get used to the questions there. So string of length 120 centimeters oscillates in fourth harmonic. Max amplitude is 4 millimeters. Find the minimum distance between the points with amplitude 2 mm. Maximum amplitude is for antinode. So that guy is going with 4. That means all particles are going between 0 to 4. So the question is, so there are particles which are oscillating only up to 2 mm. So there are multiple of them. What is the minimum distance between them? After today's class, you can start doing like waves on a string. Like I'll send you a sheet also. But, if you're doing HCV, there is one full chapter on this. I think there are 50 questions. You should definitely start doing it. It's a good thing. Everyone should try. Anyone not clear with anything, please ask. Mm, nay, Samyak, you fell into the trap. Let's see. So 120 centimeters, fourth harmonic. Matlab, there are four loops. So if you draw the picture, that is the best thing. Huh? If you can always draw the loops, right, you can actually see the data. You don't need to draw all four also, but yeah. Now, each loop is 30 centimeters. Right? Perfect. And we can clearly see here, lambda by 2 is 30 centimeters. So lambda is 60 centimeters. Perfect. Now we know the formula for amplitude is 2a sine kx. And it is given the maximum amplitude is 4 mm. Matlab, the guy in the middle, the antinode, this guy will have an amplitude 2a, and that was 4 mm. So the maximum amplitude belongs to the antinode. Perfect. So now you're saying find a point with 2 mm, right? So this would be 2 mm is equal to 4 mm sine kx. So from here we get kx sine kx is equal to half. So we get kx is either pi by 6, right, or 5 pi by 6. So if you calculate this, kx is equal to pi by 6. So k is 2 pi by lambda. Lambda is again 60 centimeters. We get x is equal to 5 centimeters. Now, what is this exactly? Now, listen carefully here. That means when you take x is equal to 5, there's a point here which is giving you 2 mm at x is equal to 5. By symmetry, I also know there is one more point here on the other side, which is 5 centimeters from that side. This is 25. I also know there is one more point here at x is equal to 35. So from a node at a distance of 5 centimeters, there are points with 2 mm. This would be x is equal to 55. You can keep doing this. Is this picture clear? So from a node at a distance of 5 centimeters, there is a point with 2 mm amplitude. Now read the question. Find the minimum distance between them. What is the distance between 5 and 25? 20 centimeters. What is the distance between 25 and 35? 10 centimeters. I think Samyak got the same thing, I guess. Right, Samyak? You are right, actually. So what is the answer? 20 or 10? 10, right? Is that making sense? So if you take both the points in the same loop, then the distance would have been 20 centimeters. But if you take the 2 points of 2 mm in the alternate loops, the distance is smaller. Is that making sense? So at a distance of 5 centimeters from the nodes, you will find a point of 2 mm. So yeah, that's the main catch there. So the minimum distance would be 10 centimeters. Because if you take the 2 points in the same loop, you will think it is 20 centimeters. That's not the minimum distance. Hmm. Right, Aditi. Right, Samyak, we have there. All clear with this? Understood how we did this? We're just using the formula like, if 4 mm is the maximum, that is 2a. Where is 2 mm? Just an equation and we got the thing from there. Let's see a few more. If you see all these questions, right, like 3 to 4 lines or 3 to 4 steps, like this is how they'll frame mains questions. Let's get these three. Look at the first one. A 75-meter string is fixed at both the ends, produces resonant frequencies 384 and 288. So these are also called resonant frequencies or resonance, without there being any other resonant frequency. So it is clear. So between these two frequencies, there is nothing else. Matlab, these are two consecutive harmonics. Now, I don't know which one it is, but you can easily guess this. The difference between them must be one harmonic. So 384 minus 288 is fundamental frequency. So done. Once you got the frequency, you can use the formula and finish it off. But let's do it anyways. So frequency is 288 is equal to, let's say, n by, I can use the formula nv by 2l, same thing. Whereas for 384, this is simply n plus 1 b by 2l. So if you just divide them, you will clearly can see if you subtract them, you'll end up with this. We get 96 is equal to v by 2l. Length is given, from there you'll get v ka value, which is 3 by 2, 24, right, into 96. That's 144 meters per second. Subtract them, you'll get this. So a string of length L is fixed at both ends. It is vibrating in third overtone. Third overtone matlab fourth harmonic, 4 loops with a maximum amplitude of A, the amplitude at distance of L by 3. So basically this is 4 loops. So implies 4 times lambda by 2 is equal to L. So we get lambda is equal to L by 2. So K ka value is 2 pi by lambda. So this will be 4 pi by L. That's your k ka value. Next thing, we know the formula for amplitude. Amplitude is 2a sine kx. But it is given in the question, the maximum amplitude was small a. Matlab, this value was small a. He is asking amplitude at a distance of L by 3. So this would be a sine k is 4 pi by L into L by 3. That is sine 4 pi by 3, which is sine 120, which is root 3a by 2. Hope you're getting these questions. Like these are like pretty straightforward. Like you just put the formula and you get the answers. A cord attached about to an end of a vibrating rope divides into 6 loops. So sixth harmonic when tension is 36 newtons. The tension at which it will vibrate is 4 loops. So again, the formula F is equal to N by 2L root over T by mu. So frequency is same. Number of loops are changing, tension is changing. So N into root T is constant. So 6 into root 36 is equal to 4 into root T. That would be 81 newtons. Straightforward questions. Like these would be like mains, this will be very easy, but CET and bits level questions, these are not everything. They do ask few of them. Yeah, just playing with that formulas. You see that major two formulas. Y is equal to 2a sine kx cos omega t. F is equal to N by 2L root T by mu. They are the two major things. All clear with the steps? Any doubts on these three? Clear, na? Vedika? Vanchika? Shreyan? Pratyasha? Devanshi? Clear? Kaivalya? Kashyap? Clear, na? Yeah. Let's see next thing. I think this guy, I guess. Yeah. So look at the question. A sonometer wire has a length of 114 centimeters between fixed two ends. Where should the two bridges be placed to divide the wire into 3 segments? So you divided this wire here. This is one segment. Let's say L1. This became second segment, L2. This became the third segment, L3. So basically you have created 3 different sonometers. So you created 3 different lengths. So there are 3 different sonometers. So the question is, where should you keep these bridges? So let's say the left side is x is equal to 0 and the right side is x is equal to 114 centimeters. So where should I keep these bridges? These are the bridges. So that you get a fundamental frequency 1 is to 3 is to 4. So if I draw the picture, this is how it looks. So this is x is equal to 0. The bridge will be somewhere here. Let's call it B1. Bridge will be somewhere here. Let's call it B2. And this is x is equal to 114. He's saying the frequency is 1 is to 3 is to 4. Then basically is indirectly asking you find the length of each segment. It's a good one. So let's see the thing. One thing is clear. See, first thing, there are a few words here. He said it is a fundamental frequency. Matlab n is equal to 1. Now, if you look at the formula, so f is equal to 1 by 2L root over T by mu. Tension is same, mu is same because it is the same string. So f is proportional to 1 by L. So that means I can go reverse. L1 is to L2 is to L3 will be in the ratio of 1 by F1 is to 1 by F2 is to 1 by F3. So that would be 1 is to 1 by 3 is to 1 by 4. That would be 12 is to 4 is to 3 ratio. So L1 is to L2 is to L3 is this ratio, 12, 4, 3. So once we got this, so L1 is to L2 is to L3 is 12 is to 4 is to 3. So L1 will be, you know how to get the ratio. Take 12 and add all of this, 12 plus 4 plus 3, into the total length, 114 centimeters. That would be 19 into 114. This is 19.6, so this is 72 centimeters. Similarly, L2 will be 4 by 19 into 114. That would be in 24 centimeters. Be careful, this is not the answer. Now, if you look at that thing, x is equal to 0, you kept the bridge here, B1. So you're saying this length is L1. So this coordinate will be 72 centimeters. That is okay. The second bridge is here, and you're saying this length is L2, which is 24 centimeters. So 72 plus 24, I think this guy will be 96 centimeters. So that is the answer. And the third one is x is equal to 114 centimeters. He didn't ask you for the length of the strings. He's asking where should the bridge be placed. You should place the bridges at 72 and 96 centimeters. Are you clear what is being asked? So be careful with that words, nothing much. If you accidentally, if you substitute 72 and 24, you're gone. Right, Samyak. Right, Naisha. Utsa got it. All clear with this. There, if you see, right, I'm not doing anything new. We are just playing with that one formula there. That's what I'm saying. Do start solving as soon as possible. Don't delay it more. All you need is some like 40, 50 problems. We practice the whole waves on a string. You'll be very good at it. So don't delay it more. Any doubts on this? All clear what we did? Next one. Let's start doing something more, a little higher. Let's say we have a composite string. So we have a thin string and a thick string. So this is 4 mu length L. This is a 9 mu length L. This side is connected to a block. So on a sonometer, someone has connected a composite string. The right side is fixed. Left side is connected to a pulley. So this is a stationary waves on a composite string. Composite string meaning you have connected two different strings. This point here is your interface. The length of the strings are same, only mu is changing. They can actually even change the lengths also, but ठीक है. Find the frequency of the second harmonic for this system. Find the frequency of second harmonic. Again, remember, what is the definition of harmonic? Listen to the word. What is harmonic? First frequency, fundamental frequency. The minimum frequency for which the stationary waves are generated on a string is called fundamental frequency. That is the definition of it. Second harmonic is what? The multiples of fundamental frequency are called harmonics. So first you need to understand what frequency generates stationary waves on this. What do you mean by stationary wave? Remember last time I showed you the video, it was forming that loop kind of structure. It should form like that. That's a stationary wave. If you don't get that loop kind of structure, you're not getting a stationary wave. So let's see how will you think about it. Think about for a minute or it's a good one. It's not difficult, but you should know. So what is the catch in this kind of questions? So all you need to think is this. Forget about the stationary waves. What happens in a composite string? When a wave comes from the left or right side and comes to the interface, you get a transmitted wave and a reflected wave, isn't it? So the problem is this. Every time the wave comes and hits the interface, you get two waves. And you get two waves of different amplitudes, isn't it? And these two waves of different amplitudes will mess up the whole thing. Matlab, every time the wave comes, you get two waves, and you'll not get a stationary wave. So what is the problem? The problem is when that interface tries to move, you get multiple waves. Look at the word there. The problem is when the interface moves, you get a transmitted wave and a reflected wave. What if it doesn't move? So that's the catch in the question. So that means the only way you can get a stationary wave here is if somehow that interface becomes a node. That means if the point never moves, then can I treat this like a fixed point, like a wall, and solve it as two different sonometers? You're getting it? So that's the whole catch in a composite string. The only way you can generate stationary waves on a composite string is if that interface becomes a node. Or else you'll always get a transmitted and a reflected wave that's going to mess up the whole structure. So, and once you figure that part out, then it is done. You can treat both of them as two different sonometers. So for stationary waves on a composite string, the interface must be a node. That is the thing that you should figure it out. Because if interface moves, it generates transmitted and reflected waves. So there'll be like three waves moving every time. It's messed up. Pi by 6. Let's see, Nish, I could be right. So now, so what are the catch then? We can clearly see tension is same in both of them, right? Length is same here anyway. So let's write the formula. Frequency is same. It is the same frequency. So it is N1 by, we don't know how many loops were there, by 2L root over tension by 4 mu. This must be also equal to N2 by 2L root over tension by 9 mu. So from here we get N1 by N2 is 2:3. So look at the meaning of this. When the stationary waves form on this system, they should always form the loops in the ratio of 2:3. So what is the first possibility? Or the first harmonic or the first possibility? So the first possibility is when the left loop is forming two loops and the right is forming three loops. That is a common factor. So the first harmonic of composite string. So remember, we have two conditions now. One, this must be a node. Interface must be a node. The right side must be a node. This is the condition you have to satisfy. Second condition, the loops must be always 2:3 ratio. That means the first harmonic, now it will look like this. So there will be two loops here. And there will be three loops here. This is your first harmonic. That means N2 is 3 and N1 is 2. So the second harmonic of the left string and the third harmonic of the right string is the first harmonic of the composite string. Is that making sense? So when you take two loops and three loops, that is the first time both the waves will agree that this point is a node. I hope that making sense. It is like saying like this, 3 and 4, what is the common factor for them? 12. 12 is the first number where both can divide. Something of that sort. So this is your first harmonic. You want to find the frequency. So F1, just substitute 2 there. So 2 by 2L root over T by 4 mu. Or you can even substitute 3 there. So 3 by 2L root over T by 9 mu. It is the same thing. So yeah, so this would turn out to be whatever is that value, 1 by L root T by mu. This is your first harmonic. I didn't ask you this. I asked you second harmonic. So what is the second possibility? Now remember, the ratio must be 2:3, meaning this can also be 4 by 6. So the second possibility, you will have 4 loops here. That means the fourth harmonic of the left string and sixth harmonic of the right string is the second harmonic of the system. So the second harmonic F2 will be again 4 by 2L root T by 4 mu. Actually, by now you can guess it, right? Multiples of this. So directly you can say that. That would be, 2 times F1. There's no need to solve. Once you got the first one, you can say multiples of this. Is that clear, everyone? But tell me one thing, what if? So if you got N1 by N2 is equal to root 2, what does this mean? This is an irrational number, right? You will never get an integer. This implies you cannot generate stationary waves. No matter what you do, stationary waves can never form on this system. So that is the thing. So be careful. It has to be a rational number. It has to be something like P by Q form. If you got something like roots, that means what it is telling you, boss, what you're asking, generate a stationary wave, I can't do that. Is everyone clear with the composite string? So at this particular frequency, F2, the left loop will say I'm in fourth harmonic. The right loop will say I'm in sixth harmonic. But this is the second time they both agree the interface is a node. So second possibility of a system. Is this concept making sense? Clear what we did? So we play with the number of loops there. If they ask you for third harmonic, then yeah, the next loop. So 6 into 9 loops and so on. You can play the game. Any doubts on this? It's a good one, little different. Again, not too tough, but yeah. Then the next thing. Now you see questions are changing, right? So we are going away from mains now and we are slowly entering that. Again, they're not lengthy questions, so it's a little different though. So we have a free end. Hope you remember the massless ring. So you constructed a sonometer where the right side is not fixed. It's a free end. Mass M and yeah, all that thing is same. X is equal to 0, X is equal to L, and the string is mu. Find the frequencies or find the harmonics. Find the frequencies for the stationary waves to form. So this is a sonometer where the right side is not fixed. Let's see how will you handle this. Find the frequencies for stationary waves. For which stationary waves form? Meaning sonometer में what are the frequencies? N by 2L root T by mu. Na? These are all the frequencies. N1, 2, 3, so on. ऐसा एक general formula आएगा. Let's see how will you handle this. So again, if you go back to the story of the sonometer, right? How did we start the whole game? Look at the story, how we did that. So in this sonometer, right, if you see the first possibility was this, the only condition is the left side has to be a node, right side has to be a node. And then we said, as long as these two are nodes, you can do whatever you want. Then we said the first possibility, we can have one loop. Then we said we can have two loops because those two are nodes. And then we said there are three nodes and so on. We just kept on playing like this, saying like, as long as you kept these two as nodes, you can do anything you want. Same way, now the only condition is, now remember, this is a free end, right? So this has to be an anti-node and this has to be a node. Is that making sense? The free end has to be an anti-node. And why? Think of this way. When a wave is entering, see what happens. As this wave is coming here, the wave which gets back, right, will be also in phase. So when half of the wave gets reflected, the reflected wave also will look like this. Now see what is happening. The reflected wave is pushing by A. The incident wave is also pushing by A. So the resultant will actually look like this 2A. So the free end will have an amplitude of 2A. Now you tell me, in a stationary wave, which points have double amplitude? Antinodes. So that is the catch in a free end. So a free end always has to be an antinode. A fixed end always has to be a node. So from there, we start the whole story again. So free ends must be antinode. Now, what is the first possibility? So first possibility, if you have a node and an antinode, means you get an half loop. This is how the picture will look, everyone. Again, what is the meaning of this? Remember, these are different positions of the string. This is T1. Next moment, you become like this. The ring becomes like this. This is T2. After some time, the ring becomes this flat here, the string T3. After some time, it starts going down. This is T4. And then eventually, you'll come to the other extreme position, T5. This point is a node. So left side is fixed, but the right side is going up and down. And we know the length of one loop, half loop, is lambda by 4. Node and an antinode. So we get lambda by 4 is equal to L. And then we know frequency is equal to V by lambda. So we get the first frequency is V by 4L. This is the fundamental frequency or your first harmonic. If you see, this is half of the sonometer thing. This is the fundamental frequency or first harmonic. So this is how it will oscillate. If you have a system like this, the left side will be fixed and the right side will keep going up and down. What is the second possibility? This is where it starts becoming a little different. So the second possibility, you can't have one loop because the right side has to be a node. So the only way you can have this is you can have one full loop and you can have an half loop. This is the second possibility, 1.5 loops. That means this will be lambda by 2 and lambda by 4. So 3 lambda by 4 must be equal to length of the string. So when you do the frequency here, F3 will get V by, so lambda will be 4L by 3. You end up with 3V by 4L. This is 3 times F1. This is your third harmonic. There is no second harmonic. You cannot generate second harmonic on this. And this is the first frequency after the fundamental. So this is called first overtone. This is the reason why overtones are defined. So overtone ka definition is very simple. After the fundamental, whatever you hear next is the overtone. You're getting the catch? So after the first possibility, which is this frequency, there is no F2. You directly got F3. You got 3 times the F1. What is the definition of a harmonic? Harmonics are multiples of fundamental frequency. So whatever is the fundamental frequency, uska multiple of it is called harmonic. What is overtone? The frequencies which you hear after the fundamental are called overtones. So let's see one more possibility, the third possibility. Remember, you have to satisfy only one condition. The left side has to be a node and the right has to be an antinode. So that means we'll get a loop, we get a loop, and we get an half loop. So it is always like that. Half loop, 1.5 loop, 2.5 loop, 3.5 loop. So it's a fraction of that. So this would be lambda by 2, lambda by 2, and lambda by 4. So if you try to do this, we get 5 lambda by 4 is equal to L. This frequency will be F5, which is 5 times V by 4L, which is 5F1 there. This is the fifth harmonic, but the second overtone. This is the second frequency after the fundamental. So you have to be really careful when they're asking overtones or harmonics. Because in sonometer, second overtone is third harmonic, but you have a second harmonic is fifth, second overtone is fifth harmonic. And this idea is important. In sound waves, we are going to do something called organ pipes. Exact same concept we are going to use there. So it looks repetitive. Instead of a string, there will have a pipe. So the general formula is this: Fn is equal to 2n plus 1 V by 4L, where n ka value starts from 0, 1, 2, 3. N is overtones. I don't remember this formula. I generally don't use this. I always draw the shape. There's a third overtone meaning seventh harmonic. Then I know it is 7 half loops. I just do it like that and derive the formula on that spot. But yeah, if you want to remember, you can remember. This is not a general formula. The sonometer one is a general thing. So the important thing here, even harmonics are missing. In this system, you can never generate even harmonics. Is this clear, everyone? Any doubts on this? Next one. We have a stationary wave. X is equal to 0, X is equal to lambda by 2. This question would be a pretty good one. Y is equal to 2a sine kx cos omega t. This is the general equation, let's say. So if a wave is moving, there'll be an energy inside. Find the energy of one loop, or find the total energy stored in one loop. Now, if you remember the formulas which we derived for a segment, they're still valid. These formulas I never derived for a stationary wave. I derived it for a string. What is the formula? Of T dx dou y by dou x whole square. If you just want energy in a loop, right, there's a very easy way to do this. I'll do that also. But this question is really important. Like, they can ask some really good theoretical advanced questions on this. They have never done that before, but don't know. They'll do it some time, some year. Half mu dx dou y by dou t whole square. Just to give you one thing here, for stationary waves, these formulas are valid. But if you remember, in a progressive wave, we proved both are equal. Potential energy for a segment dx is not equal to kinetic energy of a dx. So they are equal for progressive waves, not for stationary waves. So in a progressive wave, potential energy of a segment and kinetic energy of a segment are equal. In a stationary wave, even that is not true. So that's a formula there. So let's do this after the break. Take a break, come back by 9:40. We'll continue from here. Any doubt so far? Chalo, come back by 9:40 then. Yeah, let's give it a try, everyone. So you're asking for energy for a loop. This is dx is a energy for a segment. So substitute dou over dou x here and integrate for limits from 0 to lambda by 2. That's how we do that. But yeah, take a minute or two. Give it a try. Let's see if you differentiate what you get. Try. I'll give you 2-3 minutes. Then I'll start showing you. But you continue doing, because by the time I write and do everything, that'll take another 3-4 minutes. So easily you'll get 5 to 6 minutes. Brute force, huh? Max. There is nothing there to think. Put the formula there and integrate from 0 to lambda by 2. I'll teach you a very easy way, which you'll get it in 2 steps. But like I said, all that analysis, right? Theory, what happens within that loop, we will miss out on that. So we need to do that also. Let's see. Let's start this thing. It's if you're doing great, or else follow me here. So potential energy for a segment dx is half tension dx dou y by dou x whole square. And we also know v wave is equal to root over t by mu. So tension will be mu into v square. So this will be half into mu into v square dx. When you do dou y by dou x, you're differentiating with x, so time is constant. So k comes out. You end up with 2ak sine kx becomes cos kx. Uh, you don't mess with omega t because that is depending on time, so that remains the same. Cos square, that was the function there. And we also know v is equal to omega by k. So omega is vk. So if I substitute that, you end up with 2 mu a square omega square. Kind of, it looks like that, which we did before, cos square x cos omega square omega t. This is the potential energy for a small segment. It is changing with x and time. Same thing if you do for kinetic energy for a segment dx. Half mu dx dou y by dou t whole square. This would be half mu dx. When you differentiate with time, now you're differentiating partial differentiation with time, so cos omega t will differentiate. You end up with 2a sine kx. There's an also omega. This cos omega t becomes sine omega t. Now, if you notice this, they kind of look same, but this is sine square kx, sine square omega t. They're not equal. Did you see? This is what I said. Now, if you try to add both of them, the total energy for a segment dx, you might think like, oh, kuch to cancel, they'll become constant. No, they won't become constant here, because look at that function, how it is looking. Cos square kx, cos square omega t. There is no way to simplify this. Plus sine square x, sine square omega t. This is not constant. That is how the function looks for a segment. But there is one exception, and this could be a really good question. In a stationary wave, there is a segment whose energy is constant. So that one exception is, suppose if kx becomes equal to pi by 4 or 3 pi by 4 or any multiple of pi by 4s, then interestingly, what will happen? Then cos square x and sin square x will become equal. That is the only exception there. When they become equal, the both will come out. Then your function becomes 2 mu a square omega square cos square x dx. Then now you get sin square omega t cos square omega t. That becomes 1. Maybe I should do it in the next page. That's a really good question. Like, they can ask you the potential energy of us, any segment in a stationary is not constant, but there is a particular point which becomes constant. So this is 2 mu a square omega square cos square kx dx. So this is constant. So where are these points exactly? So if you say kx, so that is 2 pi by lambda into x is equal to pi by 4. Pi will cancel. We get x is equal to lambda by 8. So that means in the loop, these are exactly between the node and antinode. So this is your antinode. This is your node. X is equal to 0. This is x is equal to lambda by 4. This point here, lambda by 8. This point here, 3 lambda by 8. So these points have constant energy. These are special. No other point has a constant energy. But if you take a small segment at these positions, you have a constant energy. But there. So that is the total energy for a segment. So far clear? So there are multiple things here. I'll show you all those questions they can ask you in this. And then if you take it ahead, this is for a total energy of a segment. So if you want for a loop, total energy of a loop will be 2 mu a square omega square cos square omega t integral 0 to lambda by 2. You have to integrate dx cos square kx dx plus sin square omega t integral 0 by lambda by 2 sin square kx. And I hope you know this thing, sin square and cos square, the average value will be half. So if you actually integrate this thing will end up with lambda by 4, and this thing comes out to be lambda by 4. Hope you know how to integrate them. You will write them as 1 minus cos 2 theta by 2, and then you integrate it. Right? So that integration, I'm leaving it to you. So when you do that, both of them will give you lambda by 4. And this comes out to be 2 mu a square omega square lambda by 4. And now suddenly you get cos square omega t plus sin square omega t. Now again, try to understand. This would be the kinetic energy of the cos square was a potential. This term is the potential energy of the loop, not a segment. This is kinetic energy of the loop. Total is constant. That would be half mu a square omega square lambda. So in a stationary wave, the energy in one loop is constant. Energy of a segment is not constant. Each segment has different energy, but if you look at the whole loop in one go, that is constant. Everyone clear with here so far? This is one way to do, right? It's a little mathematical and lengthy. And there's a much better way and a faster way. Listen to this argument here. The alternate method. You just want energy in the loop, then you need not do all the story here. So a stationary wave is nothing but a combination of two waves. So Can I say like this? So wave 1 is entering from left side, wave 2 is entering from right side. What is a wave? A wave is nothing but transfer of energy. That means this wave 1 is injecting power, which is half mu a square omega square v wave. Meaning this much power is coming from left side into the wave. Similarly, this much power is coming from right side into the wave. Half mu a square omega square v wave. Right? And what is the length of this loop? Lambda by 2. That means for this wave to cross this loop, it will take certain time. Time taken for wave to cross the loop will be lambda by 2 by v wave. Meaning for this much time, the power is entering inside. I'll give a crude example. Think of like this. Let's say we have a room, okay? We have a group of soldiers or people, right? They're walking continuously like this. So these people are walking left side here, and there is another group of people who are walking this side. Okay? Let's say they're going with a speed of 1 meter per second. They're also going with a speed of 1 meter per second. Now, as they're walking inside, when the first person enters here, let's say the length of this room is 10 meters. So tell me one thing. When the first person entered the room, for the first person to leave the room, how long will it take? 10 seconds? Right? It takes 10 seconds for the person to enter the room and leave the room. That means for 10 seconds, whoever entered the room stayed inside the room. Do you agree with that statement? It takes 10 seconds for the person to get out of the room. That means for 10 seconds, whoever entered, everyone was there in the room. Is that making sense? And let's say if one person is entering every second, that means for 10 seconds, 10 people entered the room. 11th second, one guy will go out, but the new guy will enter. So that means net may there are 10 people inside here. Similarly, 10 people are entering from here. So in total, at any point of time, there are 20 people in the room. Is that example making sense? If every second one person is entering the room, and if it takes one person to get out 10 seconds, that means for 10 seconds, people whoever went inside didn't come out. 11th second, the person comes out and the new person enters. That means at any point of time, 10 people are there inside because of the right wave, and 10 people are there inside due to the left wave. In total, there are 20 people in the room at any instant. Is that analogy making sense, everyone? Amrita? Is that making sense? Shreyan? Param? Samyak? So the same way, instead of people, we are sending energy inside. So this is the time taken to go inside. So the total energy in the loop is the total power that is transferred inside will be 2 times into power because there are 2 loops into time. So that is 2 times. Power will be 1 by mu a square omega square v wave and lambda by 2 wave. Half mu a square omega square lambda. Same formula. Half mu a square omega square lambda. So if they just ask you find the energy in a loop, you need not do all that. You just take power and time and finish it off. Are you clear with this? That is an easy way to figure this out. And all the story that I did, we will discuss about that. All those are pretty good theoretical questions. Any doubts on this? So if you just want energy of a loop, this is the good way. Let's talk about that energy in a progressive way. Yeah, stationary wave. So look at this segment here. So when the string is at the natural length, so this is the flat part. This was the natural length. So when the string, right, has gone to the extreme position, look at the segments here. The segment at the antinode, if you see this length is dx, this is also dx. So the segment at the antinode never stretches only. If you take a small dx at an antinode, this guy is always flat. No elongation in a segment at antinode. That means for an antinode, the potential energy for the segment dx is always zero. The kinetic energy of the segment at dx, this is also zero because you're at extreme position. At the mean position, the potential energy is again zero because you're not stretching, but kinetic energy is maximum because you're at mean position. This is at mean. You can clearly see here. That means, look at data, the antinode has zero energy, suddenly it gained energy. So antinode is getting energy from somewhere. Energy of a segment is not constant. So the key point is this. Potential energy of a segment at antinode is zero. And the segment at antinode will never stretch. The other theoretical questions. Now, similarly, if you look at the guy at the node, this is dx, and look at this point here. At a node, the kinetic energy is always zero because the segment at the node will never move. The potential energy at dx is maximum because at extreme it is stretching a lot. Potential energy at dx is zero, kinetic energy at dx is also zero. So at mean position, both are zero. Node never moves, so kinetic energy of a small segment at a node is always zero. So we can clearly see from here the total energy of a segment is not constant except that one special case, lambda by 8. So now midpoints of node and antinode. So a little more on this. So how is this energy actually moving around? Listen to this. So when the loop is at the extreme position, at the antinode, the potential energy was zero. The kinetic energy was zero. Both are zero. You don't have any energy. At the node, potential energy is maximum. Your kinetic energy was zero. Now, if the string is coming back, so it is coming from extreme to mean position. It is coming back to mean. Now, when the string becomes flat, now see what happens. At the antinode, the potential energy is still zero, but somehow you gained kinetic energy maximum. At the nodes, potential energy became zero, kinetic energy also became zero. Means when you came from extreme to mean position, you lost all the energy. Now from here, you will go to mean to extreme again. So you know what is happening in this process? Energy is actually transferring from node to antinode. So energy is flowing within the segment. So when the string goes from extreme to mean position, energy flows from nodes to antinodes. So within the loop, the energy is being, transferred to and fro. Energy flows from nodes to antinodes. That's why antinode is gaining energy. And when it is going back again, the energy again goes back from antinodes to nodes. So energy is continuously flowing between nodes and antinodes. You should definitely, once revise all this stuff. It's like a lot theoretical. If you see there is not much, but these are really good questions. And they never asked before. So if I just summarize all these points. So when string goes from, I'll write on the next page. So they can ask you these kind of questions. When a string is going from extreme to mean position, energy is flowing from where to where? When string goes from extreme to mean, energy flows from nodes to antinodes. And one more interesting, if you observe, the energy will come till the antinode and stop. It will not jump across the node, meaning energy will never flow from one node to another node like this. So there is an energy transfer only within half the loop. Energy never crosses the antinodes. So technically, energy is being redistributed only in one half of the loop. Energy never crosses the antinode. So it will go from node to antinode and antinode to node. That's it. So never crosses the antinodes and nodes. It will also not cross the nodes. So energy is stuck within that half loop. Within the loop, energy is being redistributed, but the total energy of the loop is constant. And the reason why I'm telling you this much, right, is because of this. You open any book, they will always say this statement: energy of a loop is constant. They'll make this bland statement. Exam what they'll ask: what is the energy of a segment in a loop? And you're dead. You will write a constant and come, because that is the only thing you remember. So be careful. Energy of a segment is different. Energy of a loop is different. Total energy of a loop is constant. You always have to be careful. Are you talking about a segment? Are you talking about a loop? So that means if I write for a full loop, now look at this thing. If you take a full loop, the string is maximum stretched. Potential energy of the loop is maximum. Kinetic energy of the loop is zero because you're at extreme. When you come back to the mean position, potential energy of the loop is zero. Kinetic energy of the loop is maximum, not a segment. So that we proved mathematically here. There. And this was potential energy of the loop. This was kinetic energy of the loop. They're changing with time, but the sum is constant. That's all the theory of energy in a stationary wave. So if you see in this chapter, right, we talked about energy in a progressive wave also. So this energy part discussion was never asked before. So it's a good stuff like that way. Clear with this? There is one more place where they can poke it, which we will study in Bohr's theory, modern physics. If you look at your Bohr's theory, which you studied in atomic structure, we have this in our physics also, in a different way. If you remember the equation, angular momentum is quantized, mvr is equal to nh by 2 pi. If you shift it here, we get 2 pi r is equal to nh by mv. H by mv is nothing but de Broglie wavelength. So this is n into lambda de Broglie. So what this thing is saying is the circumference of an orbit is nothing but an integral multiple of lambda. So that means if you have a nucleus and if this was your orbit, so these electrons which are orbiting, right, their wavelength is forming a stationary wave. It's an integral multiple of lambda. So orbits form a stationary wave. And if you guys remember, in Bohr's theory, remember what is the name of these orbits? They're called stationary orbitals. If you go back to the history, right, the story goes like this. Rutherford says the electrons are going around the nucleus just like a planetary model, just like planets are going around the sun, electrons are also going around the nucleus. Then Bohr comes and says there is a problem with this because when a charged particle is accelerating, it emits photons and eventually the atom should collapse. You guys remember that thing? There's a drawback. Then Bohr comes and says, but there are some specific orbits. When the electron goes in these orbits, it does not collapse. And the energy of these orbits remains constant. These orbits are called stationary orbits. So the reasoning is this. So these special orbits are actually forming a stationary wave, and energy in a stationary wave is constant. That's why the electrons cannot go in whatever orbit they want. They have to go in a specific orbit. They're actually forming stationary waves. So think of like this. It is a sonometer. Instead of a straight string, it is a sonometer, which is a circle. The fixed end is here. The end is, it's a closed loop. You are getting stationary waves inside it. So therefore, energy of an electron is constant in an orbit. It doesn't collapse. That is how we can actually frame this. I think now, if you can relate the word stationary orbits and stationary waves, now you will see. Clear with this? That's how you can play around. That's a little bit about energy. That's the most important part if you ask me at an advanced perspective. Mains, I think they will just stick to maximum. They'll ask you energy of a loop or a segment. Theoretically, they'll see. Mathematically, they won't touch it. The next thing, the general equation of a stationary wave. How should a stationary wave equation look like? This is another good thing. Now, if you see the equation which I wrote, 2a sine kx cos omega t, right? It is one of the case. The general equation actually looks like this. Y is equal to 2a sine kx plus phi 1 sine omega t plus phi 2. So there are two phase constants. So this phi 1 here, which belongs to kx, it tells us the position of origin. I'll give you the examples. So this phi 1 will tell you where is the origin. Where did you choose x is equal to 0? This phi 2 tells us the position of the string at t is equal to 0. So tomorrow, if you see an equation like 2a cos kx and cos omega t, this is also a stationary wave. Don't think like, only sine kx and cos omega t is a stationary wave. So tells us position of string at t is equal to 0. Let's see how to do this. I will take a simple thing, fundamental frequency. Let's see the examples. So let's take our classic one. Y is equal to 2a sine kx cos omega t. Let's see what this equation means. First thing, what is the amplitude? 2a sine kx. Perfect. Look at this amplitude. If you put x is equal to 0, amplitude is 0. At node is at x is equal to 0. Because if you put x is equal to 0, it is always amplitude is 0. And if you put t is equal to 0, cos omega t is maximum. That means all points are at their respective maximum values. That means this is how the string is, everyone. The string is at extreme position. This is the natural length. So the string is extreme position. At time 0, the string is at extreme. X is equal to 0 is a node. This is the picture. So listen, we did two things. You took x is equal to 0 as a node. Second thing, when the string is at the extreme position, you started observing this string. You're getting it? when you write SHM, right, y is equal to a cos omega t. What is the meaning of this equation? Y is equal to a cos omega t. The pendulum is starting from extreme position, na? You guys remember that? Cos omega t implies particle is starting from extreme position. So this equation implies you started studying this string when it is at the extreme position and coming towards mean, and the origin is the node. This is the string you have studied till now. Let me take a few more examples. Suppose if someone gives you y is equal to 2a cos kx sine omega t. Now look at this. If you look at the amplitude, 2a cos kx, if I put x is equal to 0, I get maximum. Meaning you have chosen antinode as an origin. X is equal to 0 is an antinode. At t is equal to 0, everyone is at mean position. Y is equal to 0. All particles are at mean. Means if someone gives you this equation, all the particles are at mean, meaning the string is at the mean position. And you have chosen the antinode as origin. So this is x is equal to minus lambda by 4, and this is x is equal to lambda by 4. So if you shift the origin, the first part will change. And t is equal to 0, the string is at mean position. So the string is like this flat, meaning the particles are moving down. It's going to go to the extreme position now. Is this making sense, everyone? So meaning you started observing the string when it is at the mean position. Meaning, right? It forms a loop. It is exactly in the middle now. Yeah, let me take one more. Y is equal to 2a cos kx cos omega t. All these are stationary waves, right? So you can clearly see when x is equal to 0, it is an antinode. T is equal to 0 antinode, meaning the string is at the extreme position. You have chosen x is equal to 0 antinode. So x is equal to minus lambda by 4 is node. So t is 0, you're at extreme. If I take y is equal to 2a sine kx sine omega t, you're getting by changing the sign cos, you are changing everything. So if x is equal to 0 is a node, meaning the string is flat. You have chosen a node as an origin. At t is 0, string is at mean. So all these are stationary waves. Is this making sense? So now I will give you one equation. You tell me how will the string look like. So be careful. It need not be every time sine kx and cos omega t. I can take sine, sine, cos, sine. All these are stationary waves. It just means like you're taking the origin somewhere else and you're choosing the time somewhere else. So let's do this. I think if you got this, you got the hang of it. Let's say 2a sine kx plus pi by 3 plus sine omega t plus 7 pi by 4. Assume it is a fundamental frequency, means only one loop. Draw the shape of the string at t is equal to 0. This is also a stationary wave. This is another type of questions I never touched, a general equation of a stationary wave. Think, how will you do this? Let's see. So start like this. What is the amplitude? Again, the equation looks scary, but go back to the fundamentals. What is the amplitude? Amplitude is 2a sine kx plus pi by 3. Simple thing. Start from the question. What is a node? Node is a point where amplitude is 0. So take the simplest possible thing because it's only one loop. So kx plus pi by 3 must be 0. K is nothing but 2 pi by lambda. We get x is equal to minus lambda by 6. So the node is at x is equal to minus lambda by 6. That is one data point. Second thing, look at the second part here. Sine omega t plus 7 pi by 4. So if a particle is doing SHM, you can clearly see. So if this is y is equal to 0 and this is y is equal to whatever extreme 2a and uh, the extreme positions, and this is y is equal to minus 2a, you are saying 7 pi by 4, meaning this particle has gone to the extreme, then it has gone to the other extreme, and then you're coming here. This phase angle will be 7 pi by 4. Meaning if I go another pi by 4, I will reach 2 pi, isn't it? That's like 315 degrees. If I do another 45, I will reach uh, the center, the mean position again. So this coordinate y must be 1 by root 2 times minus sine of 1 by root 2 times the amplitude, which is 2a. So that means the string is at the below the mean position at 1 by root 2 times the amplitude. So there, this is the final position of the string. The dotted line is the natural length. The string is below the mean position. This would be the extreme, the dotted line. And you are at a distance of, so all the particles are at only this much of a distance. So you're at a distance of root 2a. So all the particles are at root 2 times of their displacement. And where is your origin? The node here is x is equal to minus lambda by 6. So means origin will be somewhere here. X is equal to 0. This is your anti-node. And this will be x is equal to lambda by 3. Because the total length of the loop must be lambda by 2. There, this is the string. So someone took the node as minus lambda by 6. Anti-node bhi nikal sakte ho. How much would that be? That should be lambda by 4. No? That would be 6 minus 4 to lambda by 12. So antinode will be x is equal to lambda by 12. So someone took antinode as lambda by 12, node as minus lambda by 6, and you took some arbitrary point as origin. And the string is not at the extreme, it is below the mean position, coming towards the extreme, going towards the mean position at an height of root 2a. Is this making sense, everyone? From an equation, how to pull out the data? I'll give one more like this. You try again. Let's say y is equal to 2a sine kx plus 2 pi by 3 sine omega t plus 2 pi by 3. There, draw. Fundamental frequency. One loop. So this is the general equation of a stationary wave. It can look like this. So by chance in the future you see something like this, don't get scared. Don't feel like, oh, what the hell is this? This is the stationary wave ka true form. So what we have done so far, sine kx cos omega t, mathematically there is no problem because this is simply if you change your origin and change your time, this will become whatever you want. It's just like SHM. If your particle is starting from mean position, then the SHM equation is sine omega, A sine omega t. If you're starting from extreme position, then the SHM equation is A cos omega t. If you're starting at different position, then it will be A sine omega t plus phi. The same way, a stationary wave depends on where you're taking origin and what time, where you're starting from. Your equation changes. Let's get this 120 and 120. Okay, let's see. We'll start again from there at node 2a sine kx plus 2 pi by 3. This guy must be 0. So 2 pi by lambda into x is equal to minus 2 pi by 3. So x is equal to minus lambda by 3. So you kept the node at lambda by 3. Omega t plus 2 pi by 3. That means this is y is equal to 0. You must have gone to the extreme and you're coming back here. So this must be cos 120 is minus 120, right? So sine 120 is root 3a by 2. So this is root 3 by 2 of the amplitude. So this is root 3a. That means the string is above the mean position. This was the dotted line. This is the extreme position. Your string is somewhere like this. And your center point, the anti-node guy, is at a distance of root 3a. You have taken this guy as minus lambda by 3. So this is lambda by 6. So origin would be somewhere here. Right. This would be x is equal to minus lambda by 12. Those are the position of the origin. And this guy is going towards mean position. So the string is above the mean, it is coming towards it. All clear with this? So if you get an equation with the two phase angles, that's how you play around. Now, combining everything. This would be the final question, stationary waves. Let's say we have a free end. We have the block here. Let's say this is 2 kg. This point is x is equal to minus 1 by 4 meters. The free end is x is equal to 9 by 4 meters. Mu is 2 gram per meter, mass per unit length. This guy is oscillating in second overtone. Now it is a reverse. I'm giving you data, I want the equation. Velocity of the particle, maximum speed is 10 centimeter per second. Basically, this is the particle at antinode. So in a stationary wave, the guy who goes the fastest is the antinode. At t is 0, all particles are at half of the amplitude. And coming towards mean. Find the equation of the stationary wave. Just to give an idea, what I'm asking you to find, the general equation y is equal to 2a sine kx plus phi 1 sine omega t plus phi 2. So I'm asking you to find the amplitude, k ka value, phi 1 ka value, omega ka value, phi 2 ka value. If you find these five, your job's done. There. So I combine two different things, the general equation and the free end wala thing. This is a worthy equation. Finish off, last one for the day. And with this, we'll be done with the waves on a string. Next class, we'll start off with sound waves. If you have understood waves on a string, sound waves 60-70% matches. So there it will be a breeze. Don't try to find everything. Start with something. Try to find k ka value, omega ka value. Try 1, 1, 1. You'll figure out. Try. I'll give you 2-3 minutes and then I'll show you. K is pi, omega 100 pi. Okay. Now, phi 1, phi 2 are the key ones. Yeah. But you have to find A and omega though. A, omega, and K, that should be there, I guess. Let's see. First thing, he said second overtone. So, and this is a free end and a fixed end. Remember, free end must be an antinode. Fixed end, this end must be a node. That is a condition. Start from there. Try to draw a picture. Let's see. So, first thing, second overtone, meaning it is a second frequency after the fundamental. And we know whenever you have a free end, you don't get even harmonics. So that means it is a third and the fifth harmonic. So be careful. In a sonometer, when both the sides are fixed, you get one loop, two loop, three loop. Here you get half loop, 1.5 loop, 2.5 loop, and so on. So here the picture is fifth harmonic, meaning 5 half loops. This is how the string will look like. That's your fifth harmonic. So this was lambda by 2, this was lambda by 2, and this was lambda by 4. This was x is equal to minus 1 by 4, and this was x is equal to 9 by 4. So that's, yeah, 9 by 4 plus 1 by 4, that's 10 by 4, 5 by 2 meters. So 5 lambda by 2 is 5 by 2. From there we got lambda is equal to 1 meter. K is equal to 2 pi by lambda, which is 2 pi. Perfect. Next thing, mass is given, mu is given, so V wave is root over tension by mu. So tension will be 20 newtons. Mu, be careful, it should be written in kg per meter. So 2 into 10 power minus 3 kg per meter. That comes out to be 100 meters per second. So यहाँ से V wave आ गया. If I know V wave is nothing but omega by k. K ka value is 2 pi. So from here I got omega also. That is 200 pi. No. 100 pi. V wave is omega by k. Omega. Yeah, that's 200 pi. Once you got omega, then did I mess up something? Yeah, I messed up something. This is 5 lambda by 4. Lambda is 2 meters. This is pi. Yeah, I messed up. And that would be 100 pi. Perfect. And then you said V particle ka maximum speed. And we know from SHM, V max is nothing but amplitude, which is 2a omega. So yeah, I said 2a bhi aa gaya. Vp max is given as 0.1 by 100 pi. Next thing, look at the amplitude. How to get the phi 1? Amplitude is 2a sine kx plus phi 1. And we know the node is at x is equal to minus 4, 1 by 4. So node is at x is equal to minus 1 by 4. So if I substitute x is equal to minus 1 by 4, I should get 0. So minus k by 4 plus phi 1 must be 0. So phi 1 must be pi by 4. Got it? What we did? It is given in the question x is equal to minus 1 by 4 is a node. So substitute x is equal to minus 1 by 4 and you should get a 0 amplitude. And the second part, he's saying all the particles are at half of the amplitude and coming towards the mean. Now there's a problem here. You didn't tell me which half. So there are two possibilities. This is y is equal to 0. Maybe you're going like this and you're coming back. So if you say half of the amplitude, so it's like half of the amplitude means this phase angle will be 5 pi by 6. I hope you remember that. Or there's a second possibility. You have gone up and you have gone down and then you're returning back. So this is also half of the amplitude minus half hoga 2a. In this case, the phase angle would be 30 degrees short, 330 degrees. So that's 11 pi by 6. So there are actually two answers for phi 2. Since you didn't tell me, are you above the mean position or below the mean position, I should take both. Because the question simply mentions you are at half of the amplitude and coming towards the mean. You can be above or you can be below and you can still come towards mean. Is this clear, everyone? Yeah, I got the wavelength part wrong though. There, this is how you combine everything and you get a wave equation. This is how they can play around. Sure with this. With that, we are done with waves on a string ka part. And like I said, the stationary waves was the most important thing. So please make sure to go through the notes today. We did a lot of theory. The whole chapter, if you see, right, it has a lot of theory. The mathematical functions, theory, that statement, this statement. The best way to do it, right? Don't try to remember it. Go through it once and then take a rough paper and just try to derive. It will take half an hour, but that is worth it. You will remember. That is the only way you'll remember. No matter how many times you'll read, nothing will go into the head. But this is a major thing. So next class when we catch up, we will do sound waves. That's kind of easy. That's not tough. Then we have something called beats and everything. Uh, it looks exactly like what we did right now. We also have something called organ pipes, exact same stuff. And then we'll do something called Doppler, which is removed in the mains portion, but it is there for bits in advance. So we will do it. Yeah, and after that we'll go with wave optics. So sound is not a big thing. I think we should finish off that in another 2.5 classes. But I think you should start doing waves on a string. So I'll send you a sheet also, but do start solving. Okay, with that we'll wrap up for that day. I'll see you guys on Thursday. We'll continue from here. So any doubts, anything else, please stay back and ask. I'll be free to leave.